In this presentation, we're going to be looking at reading linear graphs, which is a key, crucial thing in all science, but in physics particularly. For example, what questions could you come up with on your own, ranking-wise, with this given position time graph? So you're to rank something of the following three objects, A, B, and C, based on the graph displayed here. So first thing we need to do now, you've come up with some ideas that you might have said. You may have said something like we could rank the positions, we could rank speeds, we could rank velocities, all that fun stuff. Or if you didn't come up with that, that's okay. First of all, we have to understand how to read a graph. Basically, what meaning does this graph have? So we're going to back up a little bit and just talk about generic graphs. And we'll give you a sentence starter. This y variable here is graphed in terms of this x variable there. So if we look at the object A, for example, we can say the y variable is increasing. It's increasing from 0 at a constant rate with respect to the x variable. What would it be for C? What would it be for B? Now let's put this back into what it was. It was a position time graph with position and time. Well, let's look at object A now. So we replace y variable with object A's position. That's right here. And we still say it's increasing. That doesn't change anything. And it is still coming from 0, but now it has a very specific meaning. It's 0 meters. It's still at a constant rate. That doesn't change. And respect to time, our x variable is time. Now we use our physics, now that we've interpreted the graph, now we use our physics knowledge to be able to tell us what that means. When our position is changing at a constant rate with respect to time, we say that it is moving with a constant velocity. And if it's increasing, that means it's positive. And so this object now is moving from 0 meters at a constant positive velocity. What would that be for B?
Christian Enriquez to the front office.
Or C?
Christian Enriquez to the front office.
So a point on the graph tells us where and when at any given time. That is what we mean by instantaneous. The position can be found at any time. So one thing you could do is rank the starting points. Rank the midway points and the final positions. All right. Something else we can tell from a position time graph is velocity. The slope is the ratio of the position change with respect to a corresponding change in time. The slope is the ratio of the displacement to a corresponding time interval. We call that velocity. In fact, we're calling that average velocity, but these are straight lines, so the average velocity is the velocity. So how would we go about ranking the velocity of object A, just object A, at the starting position, at the midpoint time, and at the ending position? Rank the velocities of object A. Well, ranking velocities means we're looking at the slopes. The slope doesn't change, so the velocities are the same every single time. The slope is the magnitude and direction of the object's motion in this case. So if we were to rank the velocities of the objects, what would that come out to? Would ranking the displacements of each object give different results? What about change in velocity? How much does A's velocity change? They're all equal. They're all 0. Now let's see a different graph. Let's look at what's new. We have a velocity time graph, the same shape, the same increasing graph, the same not moving graph, and the same, not changing graph, and the same negative graph. But now what would happen if we rank the velocity of object C at the start time, half time, and end time? Now we can see something else is going on. Since we are not talking about velocity versus time, it's kind of like we're ranking the positions in the previous time. So let's go back to our basic graph reading. We're using our sentence starter, and we're saying object A's velocity is increasing from 0 meters per second at a constant rate with respect to time. We can say that the object A is constantly speeding up in the positive direction from 0 meters per second. And then we have even more concise way of saying that object A has a constant positive acceleration from rest. Another thing we can find from the velocity time graph is displacement. As you found out before, that the area underneath a curve can be useful. In particular, the area of the velocity graph, that means between the line and the horizontal axis, is the displacement. Here we have triangles, so we just have to calculate the area of those triangles. If we want to rank the overall displacement of these objects, use that technique to do that. And last but not least, if we rank the speeds of the following 3 objects based on this graph displayed here, we should now be able to answer that original question. What kind of graph is it? And how do we rank speed given that particular graph?